And welcome back to the SCI virtual event, CERT Alignment with Cyber COI Challenges and Gaps. Just a reminder, anybody that's on Twitter, be sure to follow at SCI News and use the hashtag CERTCyber to follow along in the conversation. Our next topic is using DidFail to analyze flow of sensitive information in sets of Android apps by Dr. Lori Flynn and Dr. Will Klieber. Dr. Lori Flynn is a researcher in the Secure Coding Initiative within CERT, and her work includes research and development of new static analysis and secure coding rules. Dr. Will Klieber is a researcher within CERT and author of DidFail. His work is focused on static analysis of Android apps and detection of potentially malicious Java source code. Prior to joining the CERT division, Klieber was a doctoral student at CMU's Computer Science Department. And now I would like to turn it over to Dr. Will Klieber. Will, all yours.
Thanks. I'm Will Klieber. Today, Lori Flynn and I will be talking about using DidFail to analyze flow of sensitive information in sets of Android apps. The problem that we address is the leakage of sensitive information on apps on smartphones, especially on the Android platform. Android has a complex communication system which can make it difficult to detect flows of information between apps. Malicious apps can take advantage of this. For example, suppose that you have one app that has permission to read from a source of sensitive information and another app that has internet permission. In that case, if the two apps can communicate with each other, you can have a flow from your sensitive information to the internet. So previously, static analysis tools were not able to precisely detect these types of flows. They would either have many false positives or many false negatives. The goal of DidFail, of our project, is to precisely detect these flows that happen across multiple Android components. Currently, if such a flow is discovered, the only remedy would be to refuse to install the app. But as future work, we are investigating the ability to block these undesired flows while still allowing the user to install the app and use the remaining functionality. Our tool, DidFail, takes as input a set of Android apps, APK files, and as output produces a list of flows of sensitive information. DidFail was the first published static taint flow analysis for sets of apps, not just single apps. DidFail uses a two-phase computation method, which in many common usage scenarios allows for a fast user response. Android is one of the most popular mobile operating systems in the world, with an estimated 1 billion devices sold last year. The goal of our project, DidFail, is to detect malicious apps that can leak a user's sensitive data. So, for example, a malicious app might read your list of contacts and leak that list to a marketing company. This problem is made worse by Android's all-or-nothing permission model. So in Android, when you go to install an app, you're presented with a list of permissions that the app needs, and you get to choose to either install the app and grant it all permissions, or refrain entirely from installing the app. Now, in new versions of Android that are under development, this situation is being improved, where the user can selectively choose to grant certain permissions to apps, but currently only this all-or-nothing permission model exists. Android apps have 4 types of components: activities, services, content providers, and broadcast receivers. And intent is a message sent to a component of an Android app. An intent may either explicitly designate its recipient by the name of the component that's supposed to receive the intent, or it can implicitly designate the recipient by listing properties and letting the Android OS choose which would be a suitable receiver for the intent. Components can declare intent filters if they wish to receive implicit intents. And then the Android OS matches and sent implicit intent to a receiver based on the properties of the sent intent, such as the action string and the data MIME type. Taint analysis tracks the flow of sensitive data. Taint analysis can be either static or dynamic. In a static analysis, the tool analyzes the source code of the program without running it. A benefit of static analysis is that if the static analysis faithfully models the program and the program's environment, then it can detect all possible behaviors of the program. A downside of static analysis is that it is difficult to completely faithfully model the environment in which the program is running, which can lead to both false positives and false negatives. In contrast, with dynamic analysis, we actually run the program and observe its behavior as it is running. A downside of dynamic analysis is that you can only detect properties of the program that are actually exercised in the particular traces that you execute. An advantage is that you always faithfully represent the environment because you are running in the actual environment. So our analysis, DidFail, is a static analysis, and it builds upon two existing standard Android static analyses. FlowDroid, which finds information flow within a single component, and Epicc, which identifies properties of intents, such as the action string and the data mime type, which are used to when such an intent is sent, the OS uses those properties to determine which component should receive the intent. Our main contribution is the development of the DidFail analysis and tool. DidFail is an acronym for Droid Intent Data Flow Analysis for Information Leakage. DidFail finds flows of sensitive data across app boundaries. DidFail is open source, and the source code is available at the URL shown on this slide, or you can just Google DidFail cert and it should be the first result. DidFail uses a two-phase analysis. In the first phase, DidFail analyzes each app in isolation. And then in the second phase, we use the results of the first phase to determine what flows are possible across app boundaries. We've also tested our analyzer on several sets of apps. We say that a source is an external resource, external to the app or component, but not necessarily external to the phone, from which data is read. And a sink is an external resource to which data is written. For example, sources include the device ID of the phone, the user's list of contacts that's stored in the phone, photos that are stored on the phone, the location, the physical location of the device as determined by GPS. And we also consider intents that are received to be sources. Sinks include sending information to the internet, sending a text message, writing to the file system, or sending an intent. We say that data is tainted if it originated from a sensitive source. And with DidFail, we have all sources are either Android API functions that can be called and return a value, or parameters of callback methods. And DidFail comes with a list of sources that we consider sensitive, and the user can add to or remove from that list. Let's consider a motivating example where we have a set of two apps, SendSMS and Echoer. What happens here is that SendSMS reads the device ID, and then it sends that information to Echoer. Echoer takes the device ID and then just echoes it back to SendSMS, and then SendSMS takes that data and writes it as a text message. So in effect, what's happening is that SendSMS is trying to launder the taint through the echoer. Before DidFail, previously existing static taint analyses could not precisely detect these inter-app flows. They could either have many false negatives or many false positives, depending on how they were set up. So DidFail operates in two phases. In the first phase, we analyze each app in isolation once. We use FlowDroid to find tainted data flow from sources to sink inside components, where received intents are considered sources and sent intents are considered sinks. We also use Epicc to determine properties of intents that are used in matching sent intents to receivers. Each intent sending call site is labeled with a unique intent ID. in phase 2, we analyze a set of apps. For each intent that is sent by a component, we determine which components can possibly receive the intent. We generate and solve taint flow equations, which we use to calculate the final taints of each possible sink. So let's consider a running example where we have three components, C1, C2, and C3. C1 is similar to the send SMS component of the previous example, and C2 is the echoer, and C3 is similar to C1. So let's see what happens in this example. So C1 reads data from source 1 and sends it to component C2 via intent I1. Then C2 reads data from intent I1 and sends the data back to C1. Finally, C1 reads the data from the results and writes it to the sink. And of course, C3 operates similarly to C1. So our final result is that sink 1 is tainted only with source 1, and sink 3 is tainted only with source 3. Now let's describe some notation that we're using. We write we write source arrow sink to denote that there is a flow from source to sink, and we write the component in which the flow happens above the arrow. As shown in the slide, an intent is identified by a tuple of 3 items: CTX, which is the component that sends the intent, CRX, which is the component that receives the intent, and a unique intent ID. So each line of the source code that can possibly send an intent is labeled with a unique ID. Next bullet point on the slide. If you have an intent R, then we write R of I to denote the result, the response that is sent for that intent. And giving a source or a sink S, we write T of S to denote the set of sources from which S has tainted data. So let's write the flow equations for this example. In here we have a flow from source 1 to an intent, and the intent is sent from C1 to C2, and it has an ID ID1. Then we have a flow from that intent to component C2. So it's the same intent as in the previous equation, and then C2 takes that information and just echoes it back as a response to the intent. And then there's a flow from that response that C2 sends back. C1 takes that response and then just writes that data to the sink. And C3 behaves similarly to C1. So our final result is that the taint of sink 1 consists only of source 1, and the taint of sink 3 consists only of source 3. So in phase 1, we analyze each component separately. So for C1, we know that C1 sends an intent, but we don't know who the recipient is. So as shown on the slide, we use an asterisk in place of the recipient. So we said that there's a flow from the source to an intent, but we don't know who receives the intent. So we use an asterisk for the recipient. And then we also know from analyzing the program that there is a flow from the component C1 accepts a response from that intent, and then it takes that response and writes it to sink 1. Then for C2, we know that C2 takes an intent from an unknown sender and then just echoes that information back as a response. And C3 behaves similarly to C1. In phase 2, we take the information from phase 1, we take those phase 1 flow equations and instantiate them for all possible sender-receiver pairs. So for C1, there's only one possible instantiation. The only possible recipient, the asterisk in this flow equation, is C2. And likewise, when C1 receives a response, it's going to be from C2. So we substitute in C2 for the asterisk. And the only possible intent ID is ID1 in this case. For C2, there are two possible instantiations. The first possible instantiation would be C1 for that asterisk. And the other possible instantiation would be for C3. So this single equation in phase 1 gets instantiated as two equations as phase 2. And then for C3, it behaves similarly to C1. Now, for this slide shows the same phase 2 equations that were on the previous slide. For each one of these equations that indicate that there's a flow from a given source to a sink, we generate a taint equation that says that the taintedness of the sink must be at least that of the source. So the taint of the source must be a subset or equal to the taint of the sink. So we just take all of the equations from all the phase 2 flow equations and write equivalent taint equations. And we also, for a non-intent source, we also have that the taint of that source is just a set consisting exactly of itself. And then we take all of these equations and solve them.
So in this slide, we show the processes that happen in phase 1 and phase 2. At the top, we see the phase 1, which has as input the original APK or original app, which gets transformed, and we extract the manifest from the transformed APK. We also run the Epicc tool on the transformed app, and we run our modified flow droid on the transformed app. Then phase 2 is shown on the bottom of the slide, and its inputs for each app in the taint or in the app set that we're analyzing. It has 3 inputs per app in that set, and they're just the outputs of phase 1. And in phase 2, we analyze for possible taint flows. In phase 1, we have an APK transformer that assigns a unique intent ID to each call site of intent sending methods. This enables matching intents from the output of FlowDroid and Epicc. The APK transformer uses the SIT framework to read the APK to modify the code in GIMPL, which is an intermediate representation, and then it writes the new APK back out. The reason that we do this transformation is because we had this problem. We needed Epicc to emit intent IDs, but Epicc is closed source, so we couldn't modify the code. So instead, we modified the APK. Epicc outputs information about put extras that are in intents, which are sent. So our solution was to add an extra add a put extra call with this unique intent ID to the app code directly before each intent gets sent. In phase 1, we modified FlowDroid, or we use a modified FlowDroid in phase 1. We modified FlowDroid to extract the intent IDs, which we had inserted into the APK using the transformer, and we include that in the output. When the sink is an intent, we identify the sending component, and in order to get deterministic output, we sort the final list of flows that FlowDroid outputs. The input to phase 2 is the phase 1 output for each of the apps that we're analyzing. Then in phase 2, we generate and solve the data flow equations. And And our output consists of a directed graph that indicates information flow between sources, intents, intent results, and sinks, and the taintedness of each sink. We tested the DidFail analyzer on a toy set of apps, which instantiate the example that Will was talking about in the previous slides, that running example. So we have the Send SMS app, which reads a device ID, passes it through the echoer, and leaks it via the SMS. So that's like the C1 in this figure. We have the echoer app, which echoes the data received via an intent. That's our C2. And our write file app reads a physical location from GPS, passes it through the echoer, and writes it to a file. So that's our C3. And DidFail found those flows. DidFail has some limitations, including both sources of unsoundness and of imprecision. Some sources of unsoundness are inherited from Droid and Epicc. For instance, they don't analyze native code or reflection. We also have soundness limitations due to analysis of taint flow through shared static fields. Some of those limitations have been addressed by work by Jonathan Burkett in one of our branches of DidFail late last year. However, that work currently has some scalability issues that uses a lot of memory and CPU power. So we're working on scalability issues for that analysis. DidFail does not analyze implicit flows. For instance, if receiving or sending an intent by itself conveys information aside from data within the intent, we don't analyze that. Our original release of DidFail only considered activity intents. However, we've worked with some grad students late last year who added partial support for services and broadcast receiver components. We have some sources of imprecision, which were inherited from Droid and Epicc. Additionally, currently, DidFail doesn't consider permissions when matching intents. However, we intend to add that analysis in the future. Also, currently, all intents received by a component are conflated together as a single source, and we intend to enhance DidFail's precision with regard to that in the future as well. We envision that the two-phase analysis can be used as follows. An app store runs the phase one analysis for each app that it has ahead of time. Then when a user wants to download a new app, the store would run the phase two analysis and indicate new flows. There would be a fast response to the user since our phase two is quite fast. We would use, for usability reasons, we think that policy guidance and enforcement would be helpful. So for instance, policies could come from an app store, from a security system provider, from an employer, or a user could set an option aided by an easy-to-use interface on their phone. An example policy is shown on this slide. For instance, there could be a policy prohibiting a flow from source 1 to sink 3. In the example 1 set of apps on the left, you can see that the data flows are compliant. The source 1's taint is shown as a red red arrow, and you can see that it doesn't reach the sync 3. However, the set of apps on the right in the example 2 set of apps is non-compliant. You can see that that source 1's red taint does indeed reach the sync 3. And DidFail would be able to do analysis to determine if the set of apps was compliant or non-compliant with that type of policy. An analyzer named ICTA was developed at roughly the same time as DidFail. ICTA uses a one-phase analysis for Android app sets, and it looks for taint flows. ICTA's analysis is more precise than DidFail's analysis. It's more context sensitive, and it has less overestimation of taints reaching sinks. However, our two-phase DidFail analysis allows very fast second-phase computation. The pre-computed phase 1 analysis gets done ahead of time, and then the user, when they want to install an app, they don't have to wait long for the phase 2 analysis. A typical time for very simple apps is that DidFail takes 2 seconds for the second phase, and ICTA takes 30 seconds. We are currently working with the ICTA team on a collaborative project, and we hope to develop an analyzer that has the best of both worlds, where we still use the two-phase analysis with a very fast user response, but we hope to add a lot more precision to the analysis. In order to install DidFail, you can go to the main DidFail website, which is on the CERT Secure Coding webpage at the URL listed on the slide. You can see a screenshot of that webpage on the slide. And if you click on that big red or big orange button, you get to the install and download website. There are 3 branches of DidFail. 2 of them were mostly completed last December. They're the static fields analysis branch I mentioned earlier, and the services and broadcast receivers branch, which added the analysis of those 2 components to DidFail. In the future, we plan to integrate those 2 most recent branches and simply have an argument for running DidFail to determine whether you use the static field analysis or not, since the static field analysis is a heavy user of memory and computation. And then we have an earlier version which improved DEX conversion compared to our original DidFail release, and that improved DEX conversion is incorporated in both of the most recent branches. There are 3 categories of running DidFail, and we have and you can see commands for running DidFail on this slide. The 3 types of commands you can use are, the first one is to run both phases 1 and 2 of DidFail all together, or all with one command. You can also run just parts of phase 1 separately. For instance, you can run just the transformer, you can run just the modified FlowDroid tool, you can just do Epicc, or simply extract the manifest file. And you can also run phase 2 separately after you've done the phase 1 analysis on each app. You can look at possible taint flows for different sets of apps in combination. This slide shows output from FlowDroid for the Echo or Toy app. 3 possible flows to sinks were found, where each flow indicates, or where each flow has one sink. We're going to zoom in on one of these flows, and you can see that the first item in the XML flow indicates the sink. In this case, it's a write to the log. That's followed by one or more sources. In this case, the source is a get intent. So the source was a received intent. And there's a second source for this flow as well. So there's one tainted data flow that was found to be possible to the sink from the intent, and another flow was found to be possible from the other source. Here we have the output from, or some of the output from Epicc. You can see the output lines start at 485 here. So this is output for the Send SMS toy app from Epicc. So Epicc provides precision about fields in intents which are sent. And what's found here is that there's only one set of possible values for the sent intent from this app. And those values are that the action string must be action.intent.action.send. The data type is text plain. And there are 2 extras, the new field and the secret, which for our example set of apps, that's what we use to send the tainted data.
One of the outputs from DidFail is a GraphViz file, which we can then feed to GraphViz to generate a visualization of this graph. So in this case, all the paths on this graph from a source to a sink indicate possible flows of information. So for example, here we have source 15, which is shown in the legend, corresponds to this getDeviceID function that reads your phone's device ID. And then there's a flow from that source to this intent, intent 3, which is an intent sent from one app to another app. And then from intent 3, there's another flow to sync 13. And sync 13 is this log function. And the log function is considered a sensitive source because, at least in some older versions of Android, if an app writes to a log, then other apps can also read that log function. So in a sense, logs are not private to an app. They're basically public information on the phone that any app can read. So that function is considered, at least in older versions of Android, to be a sensitive sync. And then we can show these flows here. Like here's the flow from source 15 to intent 3 to sync 13. In addition, we generate a list of flows in JSON format, JavaScript object notation. So here you can see there's a flow within a component. So we identify each flow by a tuple of 3 items: the source, the component in which the flow happens, and the sink. So in this case, we have a sink. The source is this getDeviceID function, and data flows from the source to this log function, and it happens within this one component. Here, shown in the slide, we have a flow that involves an intent. So our source is going to be the getDeviceID method of this telephony manager object. Now, when a source or a sink is an intent, we don't include a component in the second field because, in a sense, the flow doesn't really happen within a single component, so it doesn't make sense to have one here. And here, the intent, we show that it's being transmitted by this SendMS application. It's being received by the echoer, and it has intent ID 6. Here, the final flow shown on the slide, the source is an intent. In fact, it's the same intent that was a sink on the previous flow. It's being sent from SMS to echoer. And then echoer is reading that information and writing it to this sink, this log function. We also include the final taint of each sink. So the first item here is this intent, the same intent that was shown in the previous slide. And it is tainted only with this getDeviceID function. Here we consider another sink, the sendTextMessage function, which is considered a sink here. And it is tainted with two sources, this OS bundle getString, which we don't really care too much about. But what we do care about is the second source, which is the getDeviceID method of this telephony manager. We also produce excerpts from the, we also extract the Manifest XML file and use that. We use the information from the manifest in determining which possible components can receive implicit intents. So let's take a look here. I'm going to zoom in. So we have this activity component here, and we have the intent filter. So this activity component can receive implicit intents that have this action string in this data type, in this category. And I'm going to zoom in on this part over here, services. So this app also defines a service and gives an intent filter for it. It can receive implicit intents with the given action string in the given data MIME type. And this slide shows our contact information. Thank you for listening. Are there any questions?
All right, before we get to questions for Lori and Will, we got a number of questions just rolling in throughout the day asking about if the slides are available and if the archive is available. The event is being archived. An email will be sent out to all registrants within the next day or two with the location of the archive and how to access that. The slides are available now for anyone. If you just look at the webinar console, you'll see a Files tab, and you can download all the presentation files today along with other work that CERT has done in cybersecurity. So on to the first question for Lori and Will, asking from John, wants to know is, will DidFail be available for other operating systems?
DidFail is an Android-specific analysis tool. It's created for the Android lifecycle. It takes into account the Android API calls, Android sources and syncs, and Android communication mechanisms intent. So at this point, I don't think we would be able to modify DidFail for other operating systems, but
would that make it a new tool, or is it just a matter of stakeholders and funding to new research, or what would it take to draw that out to other?
Well, definitely funding is always good, and similar taint flow analysis tools could be created for other systems.
Okay. Well, and we had another question come in. What about other platforms like Linux? Could DidFail run on that?
No, DidFail is definitely specific to the Android operating system.
Okay. All right, let's get to our next question here. Let me pull them back up. And we've from Greg asking about, I believe, a tool called CyanogenMod has some privacy enhancing capabilities. How would you compare CyanogenMod to DidFail? And is there any potential for them to be used together? I guess, first of all, are you familiar with CyanogenMod? Okay. Yeah. Okay. Is there any potential for them to be used together?
Yes. So what CyanogenMod does is it enables existing Android devices. It enables the user to selectively enable or disable certain permissions, which can't be done on a stock Android phone. So the way that you could use them together is you could see if you install certain apps and there's a flow that you don't want to happen, what you can do is you can use CyanogenMod to disable permissions of the certain apps so as to disable that flow. So for example, if you have one app that reads from a sensitive data source and it communicates it to another app that then writes it to the internet, then you can either disable the internet functionality of the sender, or you can disable the functionality of the app that reads the sensitive information so that it cannot read that sensitive information.
Okay. And just one last question we have in the queue is mentioning the scale method, which I know you guys are familiar with. How does that play into DidFail, or is that a part of it? What's the relationship between the scale method, which I'm sure some of our viewers are not familiar with? How is that related to DidFail, if at all?
So DidFail uses multiple analyzers on source code or binaries in order to diagnose coding flaws relevant to security that can be mapped to the cert secure coding rules, to violations of the cert secure coding rules. So DidFail does indeed find a violation of a cert secure coding rule, which has to do with sensitive data not going to places it's not supposed to go to. However, currently DidFail is not fully integrated with the scale system, which has a web interface, and it's less. The scale system is not so much geared towards tracing data flow as to analyzing particular diagnostics from multiple tools. Do you have anything to add?
No, I think that covers it.
Okay.
Okay, that's all we have in the queue. So Laura and Will, you guys are off the hot seat a little early. We'll give us some time to set up for our final panel today, which will be our DevOps panel, which will be moderated by SEI CTO Dr. Kevin Fall, and we're going to have joining him will be Hassan Yassar and Joseph Yankel. So again, thank you guys for your presentation today. Very well done. And folks, we'll be back sharply, or we'll be back at 4:05 sharp to start the DevOps panel. So look forward to starting it back up then.